all of our differential equations problems that we solved analytically ended up with some sort of exponential in them. Now, sometimes that exponential was canceled by a logarithm, but our process for solving linear differential equations used this integrating factor, which had an e in it. I'm going to take this idea and extend it to higher order linear differential equations. Linear is going to mean the same thing it meant previously, that I could write a function of x, y prime, a function of x, y, a function of x, but now I've got a second derivative for second order. There's no y prime to a power, there's no function of y, there's no product of y or any of its derivatives with each other, they're separated. There's another word up there, homogeneous. This equation is second order and linear. Homogeneous only is when g of x is 0. So we're really only looking at equations where this right-hand side is 0. But then it goes even further, and it says, let's look at ones with constant coefficients. Well, the coefficients are the p, the q, and the r. So if I'm looking at a second-order differential equation with constant coefficients, that's homogeneous, it'll look something like this. Now you may ask, where the hell would such a thing come from? Okay. If you drive out there, the streets of Greensburg and Pittsburgh, you know what road conditions are. And it's not the smoothest track in the universe, right? This is not like driving in a giant oval where they've washed the track smooth. The road out there sucks. We hit a bounce. You hit a bump in the road. What happens to your car? Seriously, you hit a bump in the road. What happens to your car? It bounces. But it just doesn't do it once, right? You keep going. And then eventually your car settles back down. Who's here taken any physics course? I know in physics, we do this experiment where you have a spring, and at the end of the spring, you have a mass. And you measure the spring coefficient, and then you lift the spring and you let it go and you track what happens, right? In an ideal universe, with no friction, where the laws of thermodynamics and the laws of entropy don't exactly apply, if you lifted that spring and let it go, what would happen? An ideal universe. It would keep bouncing forever, right? It would go down, it would come back up, it would go down, it would come back up, without any sort of friction or enthalpy or distortion in the spring. That would just keep oscillating simple harmonic motion. I've heard that term before. It came up in one of our questions last semester. Well, wait a minute. There's a force acting on this, right? And last time I checked, that was mass times acceleration, but acceleration is the second derivative of position. There's an M there. Can't lose the M. But there's another force. The force exerted by the spring where x is our distortion. Wait a minute, I used s over here. Let's use s there. If we think of the change in position there, then we have a force exerted by the spring. Well, that's a second order differential equation. If we were in this ideal universe, then these forces would act in concert with one another, and I would have an equilibrium situation, right? That's a second order differential equation. But I'm in the real universe. What happens as I'm driving down the road and I hit a bump? Car bounces, but then it slows down. That bounce doesn't continue. A pendulum acts in the same way. This spring system acts in the same way in the real universe. Eventually, what happens? Why? Whether thinking of the pendulum, the spring and mass, or the car, why does it stop? The gravity's pulling straight down, and the force of the spring is pushing the other way, and those balance in some fashion. There's something else going on in my car. I have to get them replaced every now and then. Shock absorbers. What do? They absorb that bounce. How does that work? Okay. Anybody know anything about cars? Know what's a shock absorber do? What's a shock absorber do? Right. Because the spring that is connected to the tire is inside a cylinder full of gas or liquid that absorbs energy. In this spring mass system here in our picture, the spring itself distorts it. It actually warms up because it's flexing. We have interference with the air. We have resistance. We have some sort of dampening effect. The pendulum slows down because it's interacting with the air. We lose energy from the system. But that's related to the speed with which we move through the fluid. Whether that's the gas or liquid in the cylinder or the air in the pendulum, or the air around that mass in the spring, there's some dampening effect. And that dampening effect, damping constant, is related to the velocity. But velocity is the first derivative of position. And it should slow us down, right? So this again should be a negative. And all of a sudden my equation changes. And look at that. I have a second order differential equation. And it's got constant coefficients. It's linear, it's homogeneous, it's exactly this kind of equation with numbers there. Now, in my car, I don't just usually have one hit. I've been out there on the roads. The potholes are everywhere, the little snowbanks and the dirt on the road. I bounce all over the place, right? So I might not always have a homogeneous differential equation. There could be some sequence or some function acting on my car as I drive. That's a separate case. I want to start with the easy case where I do have a zero there. So let me think about what would happen in a second order linear homogeneous differential equation with constant coefficients. I have A, B, and C as numbers, A, y double prime plus B, y prime plus CY equals 0. I say to myself, if there was a solution for this, maybe it should look something like what we got out of our stuff from first order differential equations. Those came about with my integrating factor. So I'm going to make an assumption. Let's suppose that I have an equation that looks like e to the something x. We kept getting e to the x's, didn't we? When we did our first order differential equations, we did our integrating factor, we got e to the something. I'm going to try e to the x. Well, it might not just be 1x, it might be rx. Do me a favor. Take the first and the second derivative of that, plug it in to our equation. This one. I have to remember that when I take the derivative of e to the stuff, that's the derivative of the stuff, thank you, chain rule. And so I get an r squared and y double prime and an r and y prime, which gives me this equation, which I can factor out at e to the rx. But that's equal to 0. Wait a second. That's equal to 0. I'm multiplying things together, it's equal to 0. One of the two pieces has to be 0, right? But e to the stuff, what do you know about the graph of e to the stuff? No, the exponential is the other way, right? The logarithm goes like this. The exponential goes like this. Ah, but what do I know about the other side of it? Not the part that's going up, the other side.
Going towards 0, close to 0, and never going below it.
And never getting to it. This is never 0. So the only way for this to work is if this is 0. Okay, wait a second. What you're telling me is that if I use e to the rx for a solution, then the r's have to satisfy that quadratic equation. This means I can work backwards. And I can look and say, well, let's take the differential equation, turn it into a quadratic, and use that to find the r's. Here, is a differential equation. Second order, constant coefficients. Y double prime plus Y prime plus 12 minus 12Y equals 0. Great, fabulous, wonderful. Take that, throw out the derivatives, and replace each derivative with a power of x corresponding to the order of the derivative. So here, I will replace y double prime with x squared. I will replace y prime with x, and I will replace y with the 0th power of x, but x to the 0 is just 1. I have a quadratic equation. This is called the auxiliary equation or the characteristic equation for the differential equation. And I want the roots of that. Ladies and gentlemen, solve this quadratic equation. Are you ready for the absolute best part of this entire problem? I'm done. I claim that if I use those as our R's and I write a combination of e to the minus 4x and e to the 3x, that's the right answer. Now, the obvious answer to that is bullshit. Sure it is. Let's check. If this is y, what's y prime? Once again, the chain rule rears its ugly head. Derivative of e to the negative 4x is minus 4. But I also need that constant in there. So there's a C1 still. And here, I get 3 C2 e to the 3x. And when I do it again, because I need y double prime, I multiply again. Now let's take those pieces and put them back in our differential equation. Y double prime plus y prime minus 12y. If I'm right, we should get 0. 16c1 e to the minus 4x plus 9c2 e to the 3x plus y prime minus 4 c1 e to the minus 4x plus 3 c2 e to the 3x minus 12 times y c1 e to the minus 4x plus c2 e to the 3x. Look at what happens with the e to the 4x terms. I have 16 of them, minus 4 minus 12. That's 0. Look at the e to the 3x terms. 9 plus 3 minus 12 is 0. Holy crap. Now, it turns out that what we've created by writing e to the minus 4x and e to the 3x are two solutions to our differential equation, and then any combination of those two solutions works. This is based on an idea called independence. Our e to the minus 4x and e to the 3x are linearly independent solutions. And y equals c1 e to the minus 4x plus c2 e to the 3x is a linear combination of those solutions. And this linear independence idea is stolen from a course, I hope to no surprise, called linear algebra, where we talk about what it means to be independent. Wait a second. Think for a minute about vectors. Remember vectors? We did dot products for vectors. When was your dot product? Your dot product. Your dot product was 0. And your vectors were perpendicular to each other, right? We did that calculation in trig. Recalc. It really means that they go in different directions. Linear algebra allows me to think of functions like vectors. And these two functions operate in different, quote, directions from one another. There's a measurement of how different they are. In vectors, we do this with the cross product. Remember the cross product idea? Physics class again. Torque, the cross product. We'll do something similar. A guy by the name of Josef Wronski came up with this idea and how to apply it to functions. But this works all the time. Not if. Let be a linear, homogeneous, second order differential equation with constant coefficients. If R1 and R2 are the roots of the auxiliary equation, I'm going to throw in a new word here, the distinct roots, real roots of the auxiliary equation, two L's in auxiliary, then y equals C1 e to the R1x plus C2 e to the R2x is a solution to the differential equation. Every single time. As long as I can factor that quadratic and get two real numbers, I'm done. Try this one. Some people automatically write their auxiliary equation, instead of using the variable x, they use the variable r. That's fine. I don't care what variable you use. I want you to find the two roots. I set up my corresponding auxiliary equation. R squared plus 5r plus 6 equals 0. I factor it. Plus 2 plus 3. If it doesn't factor, rip out the quadratic formula. That's fine. Which means I get r equals minus 2 and r equals minus 3. My equation is c1 e to the minus 2x plus c2 e to the minus 3x. I'm done. That's it. I didn't give initial conditions, but if I gave initial conditions, I would need to give two initial conditions. Why would I need to give two initial conditions? My second order differential equation has information about y and y double prime and y prime, whereas my first order differential equations only had y prime and y. I need to specify, hey, our graph goes through this point, one piece. Well, now I need to specify, not only does it go through a point, I need to specify the slope at that point. If I'm trying to figure out information about y, I need to know at least two other pieces of information. With those two pieces of information, I can solve for two different constants, can't I? Remember our temperature on our spheres? We needed two different temperatures to be able to solve for the two different constants involved in that problem. Questions? I've got a question for you. What happens as x goes off to infinity?
We
Leo?
go to zero because it's the negative infinity to the y.
Which means as time goes on, this settles down. This is our shock absorber. Eventually, the ride smooths out again, right? It's a pendulum. Eventually, it comes to a stop. Our two exponentials are both negative. They're getting smaller as time marches on. That means 0 is a stable equilibrium in this problem. Try this one. I have deliberately thrown a monkey wrench into your problem. Tell me where that happens. Yeah, the problem here is that I don't get two different roots. I only get one. And I can't use the same E twice. And the reason it doesn't work is because those two solutions are not different enough. They're not independent. They point in the same direction. They're exactly the same thing, right? E to the minus 2x, e to the minus 2x. They aren't different enough. Now, again, a bunch of different people, Wronski and a bunch of other linear algebra geeks, Ørsted, Gauss and Jordan, came up with a way around this and said, what I really want is something that's just a little different. But it's got to be different enough to still be independent. And the way they got around this was to say, all right, I'm going to use e to the minus 2x. And then for this second piece, I'm going to stick in something else. I'm going to stick in an extra x. This extra x works. That was enough to make that second solution, that second part, independent from the first part. So it turns out that if I have two different roots, I use them as they are. If I have one root and it's repeated, I need an extra x floating around in the problem. I can write out the same theorem. Let ay double prime plus by prime plus cy equals 0, da, 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 right? If r is the repeated real root of the auxiliary equation, then y equals C1 e to the Rx plus C2x e to the Rx is a solution to the differential equation. Try that one. The repeated root of this quadratic equation? -3. Which means y is C1 e to the minus 3x plus C2x e to the minus 3x. And a lot of textbooks will then factor out the e to the minus 3x and write this as an exponential times a linear equation. Again, what happens as x goes off to infinity? E to the minus 3x gets really freaking small and beats out that linear equation. L'Hopital's rule. That's going to go to 0 again. Questions? But wait, there's more. I did say we were talking about springs. We were talking about harmonic motion. Okay, physics class, harmonic motion. What functions do you use in harmonic motion? Trig functions. I haven't seen a sine or a cosine yet, damn it. Where do they show up? Here. It turns out that our quadratic idea is exactly what I need to get trig functions. Write the auxiliary equation and find the roots. They're not real. I'm going to do completing the square because I think that way when I think of complex numbers. So I get r plus 1 equals plus or minus I. I get complex roots. Now, for most people, your immediate reaction should be, what the fuck? I'm going to say, the answer we want is still e to the rx. I don't care which root you use. Pick one. Let's use the one with the addition. Wait a minute. I know how to do e to the x. I know how to do e to the minus 1x. What the hell do I do with an I? Rules for exponents. If I am adding in a power, I can separate that into two separate exponentials. And now, I'm going to throw complex numbers at your face again. When we were doing power series, I pointed out to you that the power series for e, and the power series for cosine, and the power series for sine all looked related to one another. And then I wrote something about e's with i's in them. Anybody remember what that is? I called it Euler's formula. You might have done it in the trig class too. As part of this result from de Moivre's theorem. Oh, boy. Yeah. About roots of complex numbers. Euler's formula tells me that e to the I times something can be written as a cosine of that something and I times the sine of that something. So that e to the ix becomes cosine x plus I sine x. And all of a sudden, I have cosines and sines. I have my trig pieces. By the way, I said I didn't care which root you used. We used the one with the plus in the middle. If I use the one with the minus in the middle, then this would be e to the minus ix, right? So if I put the minus with the x, it becomes cosine of minus x and I sine of minus x. Wait a minute. Cosine's an even function. Cosine of minus x is the same as cosine of x. Sine is an odd function. Sine of minus x is minus sine of x. So if I do e to the minus 1 minus ix, I get e to the minus x cosine x minus I e to the minus x sine x. This is the only difference right here. Which means With a little bit more algebra, I can show that those two pieces, e to the x cosine piece and the e to the x sine piece, they're independent solutions. Notice I leave off the I. These are independent solutions to our differential equation, which means I can write y equals c1 e to the minus x cosine x plus c2 e to the minus x sine x. The minus came from the complex number. Remember, r was minus 1 plus or minus 1i. The minus 1 is where this comes from. The 1 goes in front of the x in the trig functions. So the complex number that is our root gives us our trig functions. Let ay double prime plus by prime plus cy equals 0 be a homogeneous linear second order differential equation with constant coefficients. If r equals, I need two different numbers. I've used a and b. I'm going to use Greek letters because that's what my other book did. Lambda plus or minus mu I is the complex solution to the auxiliary equation. Then y equals c1 e to the lambda x cosine mu x plus c2 e to the lambda x sine mu x is the solution to our differential equation. The absolute best part of this method is it turns solving differential equations into solving algebra equations. And it not only works for second order differential equations, it works for third order, fourth order, fifth order, any order differential equation. As long as you can solve the algebra for the auxiliary equation and find the roots. I unlock a million different applications this way. Vibrations absolutely work like this. All of our mechanical vibrations, all of our electric circuits. Remember, we did the circuit with the resistor. We did another one that had a lamp in it. We did one that had a capacitor in it. What if I put all of those in there? Then I get a second order differential equation. All of a sudden, electric circuits, pacemakers, defibrillators, neural stimulators, muscle contraction, TENS devices work because I can solve these equations. Useless, never going to use it anyway. The entire field of medicine operates on this. Drug transportation across a membrane is a second order differential equation. Nerve action because of sodium potassium ion exchange is a second order differential equation. All of the studies on Alzheimer's, all of the math they're doing for the drug treatments, what is this? Surprise! Sometimes they need more than one. There's a whole discussion on how to do simultaneous differential equations. And there's stuff what happens when the other side isn't zero. And SMA 325 differential equations is a wonderful course. It's not next semester, it's next fall or the fall after, because it's an every other year course. I think you would be well served taking it if you're interested, but that's not what we're going to do on Monday, because Monday is the review day. I would also like all of you to bring your technology on Monday, your laptop, your iPad, whatever device you use to access Canvas. I will see you all then. Have a wonderful day.